The thing that makes Hess's law so awesome is that we can determine changes in state functions for reactions we've never run before and actually don't even ever need to run from knowledge of more fundamental previously measured enthalpy changes. And this is primarily done using enthalpies of formation, which we'll make use of in the next video. But in this video, I want to talk about the general process of calculating a reaction enthalpy from given enthalpies for other related reactions. Before we get into the weeds with this, it's a mathematically and kind of intellectually demanding enterprise. You want to have a firm understanding of what we're trying to do conceptually. And in order to do that, I've color-coded the reactions in this problem, and we're going to talk through the process of structuring the solution to this problem before we get in and start messing around with the reactions and with numbers. Imagine down here that we're thinking about all of these reactions in chemical space or state space, quote unquote. We're in the purple reaction trying to take an initial state consisting of ClF gas and F2 gas to a final state consisting of ClF3 gas, 1 mole of ClF3 gas. That's represented here as this kind of purple vector in chemical space, quote unquote. We don't know that enthalpy change. What we do know are the enthalpy changes for these three reactions below, red, blue, and orange, and we can represent each of those as a kind of reaction happening in chemical space, getting us from one point in chemical space to another. The basic idea of any Hess's law problem like this is to take our target reaction in purple and kind of decompose it or figure out how it can be represented as the sum of scaled versions of the reactions we're given. So what we're trying to do essentially is take that purple vector and think about it as a composition, if you like, of the red, blue, and orange vectors, keeping in mind that we can scale and reverse these vectors as needed using the ideas that we saw in the last video, the scaling and reversing rules and how those affect enthalpy. So for example, just as a hypothetical abstract idea here, we could imagine putting the vectors together through something like this, where I've just kind of slid this vector over. The red vector is going to kind of move us in this direction, and maybe I need to scale that by some amount to move in this direction. I need to stretch that red vector in order to make this work. And maybe I need to reverse and stretch the blue vector in order to get here. And now that I've done that, the enthalpy change associated with the sum of these three reactions must be the same as the enthalpy change for the purple reaction, right? And the tricky part with these Hess's law problems is figuring out what kinds of manipulations I need to make, scaling and reversing to the kind of component or the known reactions in order to achieve the target reaction. That's going to involve some stoichiometry, a little bit of balancing the equations, and making sure that all of our addition works out so that we do in fact get from the initial state of ClF gas and F2 gas, 1 mole of each, to a final state consisting of only 1 mole of ClF3 gas. So with that conceptual background out of the way, let's get into the weeds and start thinking about how we can solve this problem. Now, I'm going to erase our sort of hypothetical abstract picture here, as it's probably not going to shake out as we color-coded things, and I'm actually going to give numbers to each of these reactions, and we'll stick with their current colors. So let's make the first reaction here red, and we'll make the second reaction here blue, and we will make the third reaction here orange. This is going to help us keep track of where those reactions show up as we add them, scale them, reverse them, etc. And our target, let's call that R, is going to stay in purple. Now, how do we even begin to express R as some kind of scaled sum of these three reactions? Well, the first place I like to look is at the reactants, the first reactant, and where does that show up? Where does ClF show up in my component or known reactions? Well, I see it right here in reaction 2. I've got 2 moles of ClF in reaction 2, and nowhere else does ClF appear. So I'm going to need to take reaction 2 and multiply it by 1/2 or scale it by 0.5 in order to construct R. So I'm going to go ahead and jot that down because I'm going to need that in my overall sum of reactions. 1/2 of 2 is going to have to be in there. We may need to do something else to 2 a little bit later on down the line. That's okay. I'm just kind of keeping track of what's been taken care of and what still needs to be done. Now, what about F2? Well, the only place F2 shows up is on the right-hand side of equation 1. So a couple things with that. First of all, the coefficient is 2, and I need a coefficient of 1 in my target reaction. So I'm going to have to multiply reaction 1 by 1/2. The other issue here is that F2 appears on the product side of reaction 1, but in our target reaction, it appears on the reactant side. So I'm going to need to reverse this reaction as well. So I'm going to need to take reaction 1 and reverse it, hence the negative sign, and scale it by 0.5 or 1/2. Now, what else has that done? Well, to appreciate that, it's actually helpful to keep a running tally of the reactants and products based on what you've written out so far in terms of scaling, reversing, etc., the known reactions. So let's do that now. For the blue reaction, reaction 2, scaled by 1/2, we're going to have ClF and half an O2 on the reactant side, and half a Cl2O and half an OF2 on the product side. Scaling reaction 1 by 1/2 and reversing it leaves us with 1 OF2 on the product side and an F2 and half an O2 on the reactant side. And in order to proceed, it's helpful now to take a look and see what's missing and how this kind of running reaction differs from our target reaction. Looks like we've got a long way to go, but it's actually not as bad as it seems. For example, we can combine this 1/2 O2 and this 1/2 O2 into just one equivalent of O2, just to simplify our lives. I'm going to go ahead and do that now. And we can see that actually in terms of chemical species, the only thing missing is ClF3. And this can provide us with a way forward, right? Noticing that ClF3 is missing, and I've got ClF3 on the reactant side of reaction 3. I want it on the product side in my target reaction, so I'm going to need to take reaction 3 and reverse it in order to make progress. So we can think about subtracting reaction 3 or adding the negative of reaction 3 in order to proceed and get ClF on the side of the equation where we need it. And so let's now add in the reverse of reaction 3 into kind of our running tally here and see what happens. We have ClF3 on the product side, 1 mole of that. We have a mole of O2 on the product side. And on the reactant side, we have 1/2 a mole of Cl2O and 3/2 OF2. Let's underline those in orange to emphasize that they came from reaction 3. All right, now let's take stock of what's going on. Again, removing any species that we can kind of subtract out and merging together species that are the same thing, just written in 2 different places, and something pretty remarkable happens. So first of all, first thing we can notice is that we have a mole of oxygen on the left-hand side and a mole of oxygen on the right-hand side. Those subtract out. That's O2 doing nothing. So let's remove O2 from both sides of the equation. We can do that since that O2 did nothing, and we can then proceed. We've got 1/2 a mole of Cl2O on the right-hand side and 1/2 a mole of Cl2O on the left-hand side. And so again, those can be subtracted out of this chemical equation and nothing of value was lost. We have 3/2 OF2 on the left-hand side, and we have 1/2 an OF2 plus 1 OF2 on the right-hand side. This is 3/2 OF2 if we think about adding those two together. So we can subtract out 3/2 OF2 from both sides of this chemical equation, and there we go. And now what are we left with? Well, if I erase the highlighting, we're left with 1 mole of ClF on the left side, 1 mole of F2 on the left side, and 1 mole of ClF3 on the right-hand side. We have constructed the target reaction. We have arrived at R as a scaled sum or difference of the known reactions 1, 2, and 3. Honestly, at this point, the hard part of the problem is over because we have figured out how R can be decomposed or expressed as a scaled sum of the known reactions. To actually solve the problem, all we need to do now is do the same thing to the enthalpies. Our understanding of how the target reaction breaks down into the known reactions gives us the instructions, essentially, for calculating the enthalpy change. So delta H for R is going to be equal to 1/2 the enthalpy of reaction for 2 minus 1/2 the enthalpy of reaction for 1 minus the enthalpy of reaction for reaction 3. And notice that this came just directly from our instructions up here. I'll spare you all the math, but I strongly encourage you to check this on your own, that the overall enthalpy change based on this is negative 139.2 kilojoules. And again, hard part of the problem is over. The hardest part of the problem was generating this decomposition. Once you've got that, it's a simple matter of applying Hess's law and doing a little bit of algebra and some plug and chug to arrive at the final enthalpy change value. These reactions 1, 2, and 3 are pretty darn complicated. And that's annoying, shall we say, right? This was a rather annoying and long-winded problem. Chemists, we're simple people. We want a simple, standard method for something like this that allows us to measure tons and tons of enthalpies, use those results systematically and as easily as possible to deduce the enthalpy changes for other reactions. This is where enthalpies of formation are going to come to the rescue. And in the next video, we'll see how to very systematically use enthalpies of formation that we know to calculate the enthalpy of reaction for any reaction involving molecules whose enthalpy of formation we know.